Okay, so I'm in Desmos right now, and I've typed in up here the general solution to the equation we just worked with. So I've got A copies, they don't have a K one, so it's A copies of cosine 4x plus B copies of sine 4x, and here I've got C playing the role of omega. Okay, so 1 over 16 minus C squared times cosine of CX. Okay, so I've got these little sliders here so that I can change the values of A, B, and C. I'm most interested right now in changing the C. I want to see what happens when C, which is the angular frequency of the forced response, gets close to 4, which is the angular frequency of the natural response. So I'm just going to slide this over and change it. It looks kind of like something interesting is happening. I want to zoom in a little bit. Whoops. Ooh, notice when I'm at exactly 4, it disappears. That's because that would put a 0 in the denominator, and we cannot have that. That would be a mathematical atrocity. Now, I'm trying to zoom in enough that... There we go. That's... Now, okay. So notice I'm at 4.1. Looks like a very interesting pattern here. It's like I've got these rapid oscillations going on, but they themselves are sort of drawing out a sinusoidal function. Right? So that's kind of interesting. Now that happens when when C is close to 4. We sort of lose that pattern as we move further away from 4 in either direction. Right? But when C is close to 4, when omega is close to 4, we've got these rapid oscillations inside this other sinusoidal sort of function. Now, if I play around with A and B, it doesn't do anything super great. It sort of just changes the amplitudes of things. But the C is what changes whether I have this pattern of these rapid oscillations sort of happening inside of a sinusoidal function. Okay, so I just wanted to show you that, and in the next video we'll talk about why that happens and how we can find a formula so that we can graph a solution that looks something like this.